Yeah, so this is going to be something a little bit different. I'm going to talk about using AI systems to make stuff. And I think, Michael, if you pass around this part, you can just have a look. So yeah, I'm going to be talking about how at NASA we're using an AI system to create these lightweight, organic-looking parts that you see on the left and right. And I'm sort of a hardcore nuts and bolts engineer, so I'm not very good at marketing. So I had ChatGPT come up with a better title for me, NASA's Next Frontier, AI and Robots Revolutionizing Spacecraft Design. So I think, that's sort of, as I go through this, even though, y'all probably can't really apply this particular thing to your career, I imagine not a lot of people making physical products here, I'm going to try to just have some lessons learned about how I've been able to apply a system to a large organization that is highly mission critical. And I think one of the first lessons learned is get good at sales, because implementing a new technology at a large organization is as much of a sales job as a technical job, and AI systems can also help you be better at selling. So it's been a little bit weird for me to get some media attention, but I think it's interesting to contrast that with some of the titles that humans have come up with. Evolved structures reduces weight and weighting, so they like alliteration. Parts look like they're from an alien starship. Language smangwage, I like this little cut at large language models. They like to throw shade. And another thing I learned is you have to be very careful about saying the word alien if you work for NASA. So the context here, this work was developed on NASA internal research money with the goal of creating and infusing into projects a broadly applicable process to really quickly make lightweight spacecraft structures. And I've done this by building and testing parts for a whole bunch of different NASA applications. And the status of this, our typical metallic part can now largely be automated. We can go from having the requirements that we want for what we want, and you see this part passing around as a good example, and have that part into fabrication in a couple days. We've been demonstrating this by test, and I'm going to show you some of the missions that it's going to be implemented in, going sort of all over the solar systems. So I want to share the lessons learned about practical implementation of generative design, generative AI. And in this case, we're improving the performance of our parts by 2 to 4 times and getting an order of magnitude reduction in the time it takes to develop them. So something that takes a month normally would now just take a few days. Something that might weigh 100 kilograms now only weighs 30 kilograms. And as you can imagine, when you're launching things into space, that's a very big deal. So I like this quote: not every change is an improvement, but every improvement is a change. And really, sort of the hardest thing, rolling something like this out to a big organization is just getting started and having the courage for that. So my inspiration for this work, came over the pandemic. I was watching sci-fi because that's something I like to do. And I'm really excited about this future where there's a lot of people living in space, thousands of people, whole industries in space. And that's really exciting to me, but then I realized that, there are 7 people that live aboard the International Space Station, and it costs about $100 billion and took decades to build. And that just doesn't scale to, sort of a civilization in the solar system. And I was really inspired by this quote from the Google CEO that AI is one of the most important things humanity is working on, as profound as, electricity or fire. So it got me thinking about how I can use AI in my field. And I think this is a good lesson for folks that maybe aren't already in the AI field. You're an expert in something, and there's a sort of a unique opportunity now to apply these tools, the tools that are available, into your field and really make an impact that you might not expect. So I came across the original DALL-E. So this is a while ago, and I was really inspired by this. So you can just have this text prompt and you get all these images, and it even does things that are creative. Like I saw that, wow, it's using the seed as a pillow. And then of course the human designer collaborates to get the ideal design. And now we know there's applications across many different industries, visual art, text, music, many things. But I'm going to talk about structural design, which is maybe something that folks wouldn't anticipate. And I'm going to talk about how you get something more complicated. So this is just an analogy. You want an astronaut in an avocado chair on the surface of the moon. To get that, you need a better prompt. And this is the prompt that I used for one of them. So I'm going to be talking about how you prompt engineer for structures. So step one is to create a prompt to digitally encode the structural requirements into software. So in the image down there, you see it's not just prompting, in this case, with text, which is information like what the loads are and how it's going to be manufactured. You're also prompting it with geometry, and I'll get into this. And we have a written guide called the Evolved Structures Guide for NASA Applications, and I think that's another lesson learned, is that it's good to, as people in your organization are figuring out how to use these tools, to have a guide that people can collaborate on and learn from each other. And then the second step is to evolve the optimal design. And that's using generative design with an off-the-shelf software package that we've tailored to meet our needs. So, I'm not really working in sort of the underlying algorithms here. A lot of that stuff is already well developed. We're just adapting it to our applications. And then the third step is to fabricate the parts directly using digital manufacturing, which basically goes from bits to atoms, and using things like automated CNC, so that's like milling, a subtractive process, and additive manufacturing, which people think of as 3D printing. So to understand how this process works, I'm just going to walk you through an application. So this is NASA's EXCITE mission. And this is a really cool mission that launches on a balloon platform. So this balloon is about the size of a football stadium. It is a giant balloon. And dangling underneath it is this telescope. And this telescope can actually look at the atmospheres of exoplanets and see what they're made out of from above 99% of the Earth's atmosphere. And it's really interesting because it launches from Antarctica. So the advantage of that is it can just keep looking, it can just keep staring at the stars and the planets without being occluded by the Earth if a satellite was orbiting the Earth. So, but this is our sort of, we can take a lot of risk in this platform. So again, lesson learned here is start with places where you can take risks. So started off really simple. We have this little bracket with some optics. We have this little part with some optics, a tip-tilt assembly, and it needs to be mounted to the back of the telescope. So very kind of simple thing, but nothing's quite so simple in aerospace. There are some interfaces here. We've got bolt patterns on the telescope. You've got a bolt pattern on a bracket. You have to avoid the optical path. You have to avoid interfering with other parts. And when this thing has done its mission, it actually separates from the balloon and drops, and then a parachute catches it, and it lands in Antarctica, and then you can go fly it again. So when that parachute catches it, there's a big load that you have to survive. And then it also has to be stiff, so it has to not vibrate too easily, or else the detector cooler is gonna shake it and blur your image. It has to be very light, because these balloons can't really lift too much. So first I'm gonna look at how a human would approach this problem. So I got a very senior designer, someone that was just retiring and not afraid to go up against the AI. But this was someone that did some of the early layouts for the James Webb Space Telescope, so very experienced. And his first design was very human looking. Our monitors are flat, so he sketched in the flat monitor and extruded it, and it was just way too heavy. So then we went again, and I told him it's too heavy, lighten it up. He lightened it up, but it wasn't stiff enough. The red shows where requirements aren't being met. And then he tried to stiffen it up, and eventually came up with a wacky design that couldn't be fabricated. And in the course of 2 days, Drew and I did 4 iterations, and we didn't meet the requirements. And I think if we had 2 weeks to design this sort of simple bracket, we could meet the requirements. But that, to me, that's too long. So let's look at how we would handle that with this generative design. So here the red is where you can't have material, and the green is where you have to have material. So the green is the preserves. So these are the bolts on the telescope, these are the bolts on the tip-tilt assembly, and you have these red areas above the bolts. That's where the bolts come in, because the AI will do stupid things like fill in your bolt holes. So that's another good example. You just have to keep these systems from doing dumb things if they don't understand the context. And then out of that, you get these very different looking designs. And this is just 4, and these are generated simultaneously by the system. And let's look at how they compare to the human design. So, it took a couple days to do 4 iterations, whereas the AI did, on a few different designs actually, 31 iterations in an hour. So it's just way, way faster. The mass is right on the requirement, because that's just sort of how the systems works. The first mode, which is really critical to us, because something stiffer doesn't tend to couple in with the vibrations of rockets and other systems. It's like 3 times stiffer. It has lower stress, so that max stress, you see these numbers are lower. That means it's stronger, considerably stronger. So it's stiffer, lighter, stronger, and it's easier to manufacture. And then we build these, put them on the vibration table, and the one being passed around is the one on the right. And they perform just as we expect. And I guess that's another good example of a sort of broadly applicable lesson. Humans make mistakes too. And you have to have a way of validating and catching those mistakes before you have a critical application. And for us, we don't really need to change the way that we validate because we already have those systems to catch human errors. So even though it's a different system designing it, it's not a human designing it, you can still validate it with the same systems already in place. And then this is sort of where we've gone with it now. The circled in green is that part was actually subsumed into a much larger part. And then here is my customer. This is the astrophysicist who's leading this mission, and he's very happy with his he calls it the alien bench. So that's just one example, and since then we've really scaled it out across our applications. Some exciting ones to talk about. In the upper right, this is the Mars sample return. So there's the Perseverance rover is collecting samples. Those are going to be launched into space, and there's going to be this like basketball-sized thing orbiting Mars, and this is going to be part of the door that opens and lets that sample in. And then there's some brackets here also that sense when the sample comes in. And then this thing that looks like an alien tennis racket, that is what pushes that basketball-sized sample towards the return capsule. And I just think that looks so cool. So there's things, there's a Venus lander, there are things going to the moon, and in the lower right you can see 2 very complicated looking parts. Those hold a whole bunch of optics, and for a human design something that holds 10 different parts like that, they'll come up with 10 different parts to hold each thing. So this is very much simpler design. And I've really taken to heart that the trick to having good ideas is not to sit around in glorious isolation and think big thoughts. The trick is to get more parts on the table. So go out and implement for real applications in your organization. So in the mechanical engineering domain, if you can get a 20% savings, people are excited. So how do you get these sort of massive improvements? And it really is because information technology has improved so rapidly. So our core pieces of software we use for engineering is something called Creo that was released in the 80s, something called Nastran that was released in the 60s. And the approach that we've taken as computers have gotten 10,000 times faster is just to have bigger models and more complex models. But it's actually a step change in what these systems are capable of when you get that kind of orders of magnitude improvement. So generative design is really an abstraction layer on top of some older technologies. Computer-aided design, which makes the models, finite element analysis, which predicts how they're going to perform, topology optimization, which is sort of the optimization algorithm, and design for manufacturing, which ensures that it can be made. So, this is another common theme, is I think a lot of the times these AI systems will be an abstraction layer that sits on top of a lot of older systems. So it really changes what the engineer does. And I think this is another theme that you'll see is AI systems will change people's jobs. So the normal process for us to design a part is you have a systems engineer throw some requirements over the fence, a designer models up a CAD model, throws it over the fence to a finite element analyst, and then someone makes a drawing and then throws it over the fence to the manufacturing people. And a lot of these people are introverted, and the manufacturing people will get the drawing and they'll curse the engineer that they don't know what they're doing, they don't know how things are made, but the only feedback they get is a high price and a long lead time. And this takes months or years because these people go on vacations, they're in different organizations, they have training. It's a very slow process. So contrast that with the process using generative design, where the AI actually generates the CAD model, does the performance simulation, and checks that it can be fabricated. And it really refocuses the engineer sort of up the stack, where the engineer is really thinking more about requirements than the actual making the models. And we've been able to demonstrate that we can go from, having the requirements known to having a part in your hand in less than 2 weeks, which for us is very fast. And there's just a GIF showing, basically how the evolution process takes place. So I'm just going to dive a little bit into that box to show what's going on there. So it starts with the user inputs, which I've already talked about. It creates a voxel mesh of the design space, so it's like essentially fills it with Minecraft blocks. It's a 3D version of a pixel. And then this is really the core underlying algorithm. It's not a deep neural network that's trained on other designs. It's actually something called level set topology optimization and compliance minimization. So there is, gradient descent backpropagation, but there's not, the physics behind this is known, so there isn't really hidden layers of meaning in it. And then the outputs of results, the outputs are shown for user review, and there's actually some machine learning that sorts those and recommends them. And then you reconstruct the CAD model, from that voxel space into a usable CAD model, which has always in the past been only a human task. And then you make it. So the digital manufacturing part is how do you go from bits, which I imagine is the realm that most of you are in, into atoms. So the image on the left there is actually just a rendering, and the image on the right is the real world. So digital manufacturing is a manufacturing process that can make physical parts directly from digital information. So there's some kind of software that takes in the CAD model and generates a program that a robot runs to make the part. So a lot of people see these parts and they think 3D printing, but that's not the only technology that can be used. So in the upper right, you see a 5-axis CNC robot cutting a part, and automated CNC is possible. It uses what's called a CAM program to generate the program the robot runs, and there's even a shop now that has 500 CNC machines and no machinists. I think this is what people are just sort of loading in blocks to the machine. So the automation is just picking up. And in the lower right, you see a laser powder bed fusion process. So that is actually printing metal parts by melting the material with a laser. So this is a bit of a newer technology, still developing, but very easy to slice your CAD model into layers that goes into that software, and then the additive manufacturing robot just guides the laser around. There's some post-processing and some challenges to that currently, but it's really rapidly developing. And the bright future of this technology that I see is for the true marriage of additive manufacturing and AI design structures, where you can get, there's going to be a lot of cost and schedule improvements as the 3D printing matures, there's more of a market, and there's more standards developing. And you can also see these really hollow parts. So that same bracket, here's a hollow version that performs better, sort of like a bone-like with internal structure. And the other thing that I'm really excited about is to have large monolithic structures. So on the lower left here, you see sort of a typical spacecraft design. And really what that's doing is it's holding a bunch of components. You can see a propellant tank in there and maybe some sensors. But to support all that, there's all this stuff that's bonded and bolted together. And I think that can be replaced with one really awesome organic structure, large thing that's additively manufactured. And then in the center here is the James Webb Space Telescope instrument platform. It holds all the instruments for the James Webb Space Telescope. It has to be super stable. And this took a very long time to design, analyze. People are manually injecting glue to build this thing up. And I think that in the future will be able to be replaced with an additively manufactured part. And you can see that sort of additive manufacturing at scale. This is Relativity Space, is a company building entire rockets with a giant robot arm that's using it's called a WAM process. So basically you can print something as large as you can get a robot arm. So some of the pitfalls and barriers to the adoption I've seen with this technology, first that there's a skills gap where design, analysis, and manufacturing skills are all needed. But in our organization and many large organizations, they're stovepiped into different branches. And what you really need for this, and I think you'll see this with a lot of AI tools, is it really helps to have a generalist, somebody that is multidisciplinary, that can see across things that are normally separate. And this can be achieved through training. It's actually can be hard to find these people that are more senior, but we've been able to train students. And I think you're going to get sometimes that 10x engineer, that Silicon Valley sort of 10x engineer idea that can get 10 times more done than average. And that's going to be very powerful for us, but also creates cultural challenges. And there's also cultural inertia, right? Just a general resistance to change, and especially for these parts because they just look weird and alien. And the key to overcoming that has been just to get all the stakeholders together and get their feedback, find out what it is that they're worried about, and then build, fly, and test lots of parts, because that's how you convince people. And there's also this fear of being replaced by AI that I'm sure will only grow with time. But with us, we need to encourage a win-win mentality, because it's not that we're going to need fewer people, it's that we're going to be able to do more missions. And also to encourage people to have a growth mindset, that learning new things is fun. And a final challenge, and this is sort of universal, is the garbage in, garbage out. You got to get the inputs right to get the outputs right. But this is where the human in the loop comes in, because one of the things I find with structures, if one of the parts is wrong, if I missed a requirement, it just looks wrong, right? Because we are sort of trained on, if you're climbing a tree and one of the branches is deformed or weak, you just know that intuitively. So the power of human intuition is still there. And then also, as I previously mentioned, you can validate with your existing techniques. And I really like this quote: when I'm working on a problem, I never think about beauty. But when I'm finished, if the solution is not beautiful, I know that it's wrong. So just to summarize, the process encodes the requirements sort of in a prompt. The generative AI evolves an optimal structure. Digital manufacturing fabricates the parts. And we can now automate making our typical metallic structures. And this is really powerful for us compared to seeing, like a car or a bike company might not have that many products, and they're sort of evolving products. But for us, there's only one James Webb Space Telescope, and it has thousands of parts. And a lot of those we'll never reuse them. So for us to be able to develop thousands of parts uniquely quickly is a big win. And the parts are more performant, and we've demonstrated it by tests. And in the future, we want to make sort of all of our structures and things like optics, apply these techniques to it, and also integrate large language models to create the inputs, take them up a level of abstraction, because these missions all start with a document that describes, an English language document that describes what the mission is going to do, what science it's going to get. And I think we'll be able to flow that down into different systems, into different AIs to help automatically generate entire systems in the future. And hopefully, those alien spaceships that you see in science fiction will soon be our spaceships. Thank you.
Thank you. Thank you for the talk. So this topology optimization problems involve big problems, like you need to simulate the thermal problem of the manufacturing system, mechanical, microstructure. Does your generative AI system include, for instance, physics-informed machine learning, like to understand from this finite element-based simulations and then kind of speeding up even further?
I'm sorry, I'm not sure I understand.
Are you also considering like physics-informed machine learning models to speed up your finite element simulations?
Right, so I know people are working on that. I haven't seen good results from it yet. Where people are really seeing big impacts from the machine learning-based models is what's called, it's like a substitute model. So for really complicated systems that take a long time to run, you have these other models that you can train, that you can make small perturbations and get the answers much quickly. So that is being done, but that's usually being done sort of at a higher systems level where there sort of are enough complexities that they're like hidden layers.
Hi, thanks for the talk. It's really impressive. Just curious on the kind of bottlenecks you're facing right now. You mentioned that it took 2 days to get your first results. What do you think would be the best improvements in the model? More compute, different software is not the most optimized.
So by far, the biggest, the tallest pole, the longest lead thing is getting the requirements. So once I get the requirements, I can usually encode them in a few hours, and then it'll run in an hour or two. And then I show it to the stakeholders, and I might not hear back for like a week or two. So, and that's really an interesting challenge because the systems engineers are used to engineering taking months, like I showed in that slide. So they want to make sure they get the requirements perfectly right before they give you the requirements. So they tend to not want to give you requirements. And I sort of have to retrain them to think about the new paradigm where you don't have to have the requirements perfect. Just give me a set of requirements. I'll make you a part, and we can iterate because the design analysis cycle no longer takes a month. Now it takes, if you get some requirements changes, it might only take a few hours. So really the long lead is working with the other people that have the requirements.
Nice, thank you. Can I do a follow-up? So the question came kind of thinking from the previous talks about open sourcing stuff. This is very impressive. It is inspiring to me, and I'm thinking how I could apply this and where this could be applied in other fields. So bottleneck came like, is this just because it's new, or can we go to different industries as well?
Yeah, I think one of the challenges is that there's a lot of research in a lot of different fields on these topics, but then not a lot of it has necessarily been productized into something that's usable. So the nice thing about the tools that I'm using is they've been productized. But I think if you're willing to do the work of getting a little bit more down in the metal of what's going on, you can find a lot of research for other fields. But it'll just take more effort because it hasn't been productized yet.
Thank you for the fascinating talk, Ryan. My question is around one of the fact you mentioned that some of the hidden layers were not needed because you already know the physics of some of these things. So I'm interested to know if PINN's physics-informed neural networks had any roles to play here. If not, what are your thoughts on integrating PINNs with the generative AI or LLMs?
Yeah, I guess I don't know enough about that to give a good answer yet. So the surrogate models is the other thing that I mentioned that people use. I forgot, now I remember the name, surrogate models. But yeah, if there are, I'd be interested to talk to you about it after.
Okay, that sounds perfect. Thank you.
Any more questions, please? Yes. So I wanted to know about, looked like there's a recommendation engine almost in the end, like you generated a bunch of examples and then yet another algorithm sort of sifted through them. So I was wondering what that process was like to figure out, what measure of good you wanted to bubble up to the top.
So there's a lot of options in that. So there's, a bunch of sliders, like do you care about cost more? Do you care about complexity more? Do you care about mass more? So there's a lot of, that's sort of a complicated question because there's a lot of different things you might want to optimize for. But in the end, a lot of times the hardest part of it is finding something that is manufacturable, because that is part of the inputs. How are you going to manufacture it? But you still really need to. It's not perfect yet, so that sort of like manufacturing knowledge is still needed.
Thank you.
So the evolved structure of that component originally it evolved to what you passed around, and then later you showed one that you said was the bone structure, and I was wondering if that the gradient descent could find that bone structure, and that was the limiting requirement, or was that was there some other approach in order to get to that space that had the bone structure?
That's a great question. The tools, so those hollow bone-like structures I think just based on sort of biomimicry, the industry has been really excited about them. But it turns out that they're not quite as advantageous as you might think, because the actual structures sometimes end up being hollow, but just not continuously hollow. So the workflow to get those hollow structures is still very much in work, and it's not using the level set gradient. It's basically what you do is you use a higher mass target, so you get a chunky part, and then you use another algorithm to hollow and fill it. But then there are also challenges with that because it's much harder to simulate because of all the sort of thin shells and members. And then it's also much harder to manufacture because you have to get the powder out. So the way that these work, when that thing is printed, it's full of powder. So you have to make sure you have holes. And so that process is not yet automated. It's something sort of in the future.
Thank you.
One more question? Yes.
Thanks for the great talk. It's very interesting. A question on the requirements that you get from, say, like the systems engineers. I'm going to assume that the launch has probably has the worst environment because of all the vibrations, right?
Right, so the launch is worse in terms of loads.
Right, for loads.
But then there are other kinds of requirements. And one of the interesting things about it is you can actually encode your internal processes into the requirements. So for instance, we have a very specific requirement that a fastener has to be 1.5 times its diameter from the edge of your part. And a lot of junior engineers will miss that and get to a review and it'll get caught. But the nice thing is that process is now written into the Evolved Structures guide. So you can encode your company's process. But some example of other requirements are, how do you deal with light paths and how to leave clearance around them? How do you deal with if you have a part that's generating power and you need to get that heat out? So there's a lot of different kind of requirements that you might have.
Okay, and sorry, to follow up the question to that would be, so did they provide, like, say, at these certain interfaces or at a certain CG of the part, you're going to face these equivalent static loads given the vibration profile? And then are those loads fed into your input when generating the structure? Or at the very end of generating the structure, is that when you use Nastran again?
Right, so that's a good question. You know something about this stuff. Huh?
Yeah, I used to do flight loads and structures, so.
Right, so we actually have something called a mass acceleration curve that relates the acceleration a part sees to the mass of the part. So it's really simplistic. It takes into account sort of historically what we've seen for structural dynamics when the rocket launches that lower loaded components are in more flappable things and see higher loads. So we have this really straightforward guide to it weighs 5 kilograms, it sees 30 Gs or whatever that you start out with. And then as you go through the process, eventually you do a couple loads analysis of the whole system and you get better loads. But one of the kind of key features of these parts is they're really strong. They only really have high loads around where the fastener is because that's where all the load goes out. But the rest of it, you don't really get any stress peaks. Just the way the algorithm works, you get this really nice, smooth sort of strain on the outside, just the way the level set works.
Cool, thank you.
Well, let's give a big hand to Ryan.